you. The first would be the computer you're watching this on, or your cell phone, or if you maybe have it connected to a TV. Lots of different energy systems that are obvious to us as we look around the room. But hopefully you saw a lot more as you were thinking deeper about it. The fact that your cords were connected to the outlets, and that those outlets were connected to power plants, and those power plants were generating power through maybe nuclear or coal or natural gas. So there are thousands of examples of energy transfer systems around us, even the smallest from the microchips that are in our computers, and they dissipate heat, and that has become a rate-limiting problem for the chips that are in our computers, to the energy densities associated with the batteries that are in our cell phones. We want to have a lot of energy, but we don't want to pay a lot in terms of the volume or in terms of the mass. So many examples that we can see all over. So what are the drivers for changing the way that we use energy currently? And I'd like to take this time to motivate you for, first of all, why we should study thermodynamics and what systems in particular we should look at in terms of power generation for many different sectors. So let's start with a review of where are we now? Well, global demands for energy are extraordinarily high. What you're seeing in this figure is a composite of some photographs that were taken by NASA. This is from their science source, and it's entitled Lighting Up the Ecosphere. But these are nighttime shots, again, pieced together around the world, and you can see the lights from North America are quite bright. You know, the high population density centers around the world you can see are quite bright, but you can also see areas that are quite dark as well. So we can see there's a lot of energy demand, and there's a lot of energy demand around the world. Now, what I'm showing you is a population cartogram, and this was actually generated by the University of Michigan physics professor, Mark Newman. And at the time, Mark was interested in trying to generate graphical ways of interpreting data. So he didn't mean to be controversial, but he produced a couple of figures here, and this is the first in the series that I wanted to share with you, that show you the population, where what he's done is distorted the size of the countries based on their population. So you can see, the United States is quite large. China and India, where the bulk of the global population currently are very, very large. And you can see that, several countries are quite small. You can see Russia has shrunk considerably. We can see a distortion here in Europe, and look at the distortion in Australia to represent the low population in those countries. In the next cartogram, here we can see energy consumption. So now we look at the places around the world and we can see a dramatic shift. So the United States is now even more bloated, further than even beyond the population. But we can see that China and India have shrunk, Russia has expanded, Australia has expanded some, but Africa has virtually disappeared, and Brazil has gone on a significant diet. So the point is that there's countries that use a lot of energy, but they aren't necessarily the countries where the bulk of the population is. So we have two drivers that we can see already. Developed versus developing nations, so industrialized nations versus less industrialized nations, and sheer population. Those are both drivers for global energy consumption. And this graph shows you the same sort of discussion or same topical points, now, of course, in a conventional bar graph form. So I'm not sure how well you can read these figures, so I'll explain them to you. Here, the axis, this is a plot of the total population by region at 4 snapshots in time, 1950, 95, 25, and 2050. 1950 and 1995, the data from these 2 years are actual data. The 2025 and 2050 data are projections of where people feel the estimates are for population growth by region. And specifically, the regions we're looking at are Oceania, North America, Latin America and the Caribbean, Africa, Europe, and Asia. And there's lots of conclusions we can draw just based on looking at this figure. First of all, we can look at what is the current population, the 1995 data, sort of current, not quite up to the year 2013. And we can see that the bulk of the population currently exists in Asia. And we can also see where is the projected growth going to occur. And we can see that the projections show that the population growth between now and 2050 is almost exclusively in developing nations, in what's often referred to as the BRIC nations, BRIC being Brazil, Russia, India, and China. And we can see, again, while we already have a significant population in Asia, that population is projected to grow by almost 2 billion people. And there are a couple of other features that we can look at. It's projected that Europe will actually lose population. We'll actually see a decline in population. Africa will see an increase. Latin America and Caribbean will see an increase too. North America is projected to almost flatline. So the point of this is that energy, as we expect, is driven by developed versus less developed nations. So industrialization does, of course, drive energy demands, but so does population growth. And population growth in Asia is expected to increase dramatically. So we expect global energy demands to dramatically increase in Asia. So let's take that information and let's couple that to the next slide. Here we have the gross national product per capita in US dollars as a function of energy use per capita in millions of BTU. And we'll talk about energy units here, but this is a British thermal unit. It's a unit of energy here. So this is increasing energy. This is increasing GMP, both on a per capita basis. GMP is generally an indicator of quality of life, sort of. And it's also a general indicator of developed nations. And we can see here, we have Japan has a very high GMP, Germany, France, United Kingdom, US, we can see are all above average. Okay. Now, I should say that these data are taken from World Bank data. This is as of 1995, so I took these data. They're available to the public and plotted these. And you have to decide, which countries you want to include when you calculate these averages. So I think I chose approximately the top 30 countries, something like that, in terms of the top GMP producers and top energy users. So you would get a different average if you included more countries, and that average would actually decrease, both in terms of GMP and in terms of energy per capita. The point being is that these developed nations are high GMP and high energy users, both on a per capita basis. And I intentionally left this a little bit hard for you to read because I wanted you to see that India and China, circa 1995, so a little bit dated, were very low GMP and very low energy use on a per capita basis. So we've already discussed how we expect to see significant population growth in these countries. We would also expect to see significant increase in quality of life and industrialization, both of which are going to move these countries in the northeast direction. So they're going to move from this quadrant to this quadrant. Those are going to be compounding effects, an increasing population that uses more energy per capita. So now what I want you to ask yourself, if population growth is projected to grow by 2 billion people in the next 50 years, how much new power would we need if each one of those people, individuals, used one 50-watt light bulb? So 2 billion people, one light bulb each. What's going to be the increase, the new energy, new power demand that we're going to have to provide just to meet